My major is in computer science, so I'm the only student in the Gunn Institute who is a computer scientist, which is fun. And so in particular, I try to work on computer algorithms for spatial analysis of ecosystem service flows and decision support systems that would use that information to try and help people who are making land management decisions get a better sense of how to target their different management scenarios, right, given cost constraints and whatnot. Okay, fantastic. And I guess I should also say that my research here has been predominantly on the ARIES project, which stands for Artificial Intelligence for Ecosystem Services, working with Ferdinando Villa, who is now in Basque Spain. His name's there. Okay, so I'm going to talk about some work, which is a core component of the way our system, the ARIES system, models ecosystem services, how it's different from what anybody else out there is doing right now, which is fun. Okay, that being said, let us proceed with the slideshow. Yes, very good. Okay, so the framework is called Service Path Attribution Networks, or SPANs. That's catchy, right? Goes from ecosystems to people. Okay, so we're talking about spatially quantifying the flow of ecosystem services from landscapes to people. That's my name, a couple of people who worked on this stuff with me, and we are coming from the Ecoinformatics Collaboratory, which means upstairs in the back at the Gunn Institute. Okay, all good things. So we can breeze through this, because you guys all know what ecosystem services are. Anybody not know at this point? Brand new, fresh people? No, you guys totally know, which is awesome.
I would have to say that I like your definition better than a lot of conventional definitions.
Excellent. We're going to dig into it. Mr. Varley, please feel free to jump in whenever you feel like it. Okay, so ecosystem services are vague. They're abstract. And they're this big list, and everybody comes up with a different list and a different classification and a different categorization. But what is an ecosystem service? How do we define it? How do we measure it? How do we assign value to it? Should we assign value to it? Should it be monetary value? Should it be something else? These are the great big questions in this field, right? But we have in this little diagram right here a couple of things that folks in this field tend to recognize as ecosystem services. So we're talking about regulating type services like soil and sediment regulation. That means avoided erosion, right? Water supply and quality is important. Food and fiber, everybody recognizes. More abstract things like scenic views under recreation and aesthetic benefits. And of course, good old climate regulation up at the top, among other things. So these might be some ecosystem services. But that's examples, but can we get down to a real definition? And how do we try to assign values? Well, right now, sort of the big state-of-the-art in putting numbers on these things are mostly done using benefits transfer and land use land cover values. So what you tend to see in some of the tools that are out there these days, which are largely spreadsheet-based tools from a computational standpoint, are folks taking typically land use land change maps. These are maps which are going to lay out for you sort of pixel by pixel or polygon by polygon what kind of land classification this is in terms of human use. So this means, is it wetland, forest, is it field, is it pasture, is it urban, is this a highway, is it some water, etc. And they take these different land use classifications and they assign some dollar value or range per land use classification type, right? And then the way you get the value of ecosystem services in some area is to simply count up the number of pixels that you have of that type, or polygon area of that type, multiply it by the value per acre, hectare, whatever you have, and then add it up. So it's a weighted sum. Incredibly simple, incredibly simplistic. But that's sort of what people do. So then look at these maps. So look, here's the water quality value, soil conservation, et cetera, et cetera, et cetera. This is what we do. Okay, pros and cons of this particular approach to ecosystem service assessment, assigning values. Pros, easy to implement, right? It's a weighted sum. How easy is that? Except for that little problem of trying to get the actual dollar value or range in the first place. But we can leave that up to Dr. Farley to keep him up at night. It's easy to understand because, again, it's a weighted sum. It's using land use maps. It's one layer. I mean, how easy is that? This makes simple scenario and trade-off analysis because all you have to do is say, okay, my policy decisions say put the wall mark there, reforest here, or maintain this wetland in its current state. So you look on the map, and all you do is change a couple of the land use values for some of those pixels, and then repeat the weighted sum. I mean, come on. Easy. So that's what scenario trade-off analysis looks like. The dollar value goes up or down in the aggregate, but it doesn't really tell you all that much about the spatial dynamics of the ecosystem services, that's entirely what we're missing here by these in situ calculations. And of course, it works just fine with the old benefit transfer secondary evaluation techniques. So that means I look in some other area, like Madagascar, and I look at some studies, some surveys or some such, that were done, I don't know, 5 or 6 years ago of some tribe, and the folks were asked in one way or another, how much do you value these wetlands or these forests for hiding your cattle or something like that? And they say, oh, it's worth this much, and then they argue about it and they come to some value range. And they put it in a paper, and some researcher says, great, I got another publication, excellent. And then later on, somebody else in Mexico says, gee, I really wish I knew what the value of these forests were in this rainforest. So they go and they look, oh, well, there was a study in Madagascar where some people were asked what the value of forests were to them 5 years ago. So they go and they grab these values and they turn around and they just copy the dollar value per acre of forest or hectare, Madagascar, right? And then drop it in Mexico and say, bam, that's the value. Except Mexicans, or did I say Arizona? Anyway, whatever. What should I say? I said Mexico. Okay, Mexicans are not Malagasy people. Okay, they have different value systems. And furthermore, a forest in Madagascar is not the same thing as a forest in Mexico. They provide totally different services, or they might provide totally different services. And this is, of course, where the critiques of benefit transfer, picking up the dollar value for some other study in a different time place and applying it over here, run into some trouble. Although, like I said, this stuff works great with them. It's easy to apply that approach. Cons. Well, ecosystem services have really important spatial dynamics, which most people don't simulate. And I'm going to talk about that in this talk in particular. And they make no distinction between what I call potential services and realized services. So this is the tree falls in the forest conundrum. All right? So you have some landscape. It's providing some services, maybe. So you got some trees along some waterway. They keep the sediment from getting in the water, and therefore the water downstream is nice and healthy and clean. And fish swim in it, and all is well. You know, deers frolic, etc. Deer frolic, no S. I don't know what happened there. Okay, except nobody lives there, and nobody ever goes through there. No human beneficiaries, no ecosystem service, just potential service. It could be tapped, but right now it's not being realized. And that's going to be missed if people just go in and say, oh, a forest by some water must have value, and assign it. So they miss this fact. And so what I want to say here with this work is that to assess ecosystem services, we need to pay attention to who the beneficiaries of the services are and where they're at, and what the paths are, what pathways transmit the service from the ecosystems provided to the people which receive it. Okay. Just to put a finer point on it, land use, land change is not the whole picture for assessing ecosystem service value in situ, because a forest is not a forest, is not a forest. They're different, they provide different services in different degrees to different people with different value systems. So, we introduce a new definition of ecosystem services. We say, ecosystem services are the effects on human well-being of the flow of benefits from ecosystems to people. Ecosystems to people, over a given extensive space and time. Right? So we're going to take that part into effect. Now, if we start talking about we need to flow a service, we can step back and think a little bit harder about what those flows might look like. And there are some abstract flows that have been published before. Here we have this paper by Fisher et al. That came out in the middle of my research that was looking more abstractly at this idea. And so P is provider, i.e. the ecosystem, and B is beneficiary in these diagrams. And we're looking at some different abstract means or patterns of service flow. So number one here is in situ flow. So this would be a situation in which, in order for a beneficiary to receive some quality of life benefit from this service, they have to be on the land where it's provided. Can anybody come up with an idea of one of those? Example. Of a number one, where you have to be at the source in order to actually receive these services.
Or cherry tree.
Shade tree. Shade from nothing. That's
Recreation, right? You have to go
recreational
to the
benefit.
park.
Yep, you got to be at the park. The park doesn't come to you. Exactly. So that kind of a thing. Perfect. Same thing. I get, if I'm a farmer, I want to get these benefits for growing things from my healthy soil. So healthy soil is going to provide me with that benefit. You can't farm on the street and get the benefit from the soil a mile away, right? You got to be at the place.
Well, beekeeping, you got to be at least a mile, within a mile of bees.
There you go. So now we've moved to number two, proximal.
For pollination.
For pollination. So if we were thinking about something like bee pollination, in this case, your provider are going to be your beehives, locations of those, P, and then your crops that want to get pollinated by them need to be proximal to the bees. So the further away you get, the more the service drops off. You can imagine some kind of a Gaussian curve, obviously modulated by some stochastic algorithm or describing how your bees want to move in that area depending upon the spatial characteristics of that landscape.
Subject to thermodynamic limits, of course.
Yes, within limits, and understanding the uncertainty and the unnecessariness of modeling things you don't understand. Number 3, well understood, hydrologic cycle type behavior, where service is generated up here, like water falls on top of the mountain, or the snow melts on top of the mountain, and then it rolls downhill. Follows paths of elevation, slope, and stream channels. It gets down here to the beneficiary at the end, right? The person who's going to take up surface water, for example. So this kind of thing, this kind of flow pattern is going to be seen in a lot of hydrologic services. It's anything from nutrient movement, cycling, like phosphorus into Lake Champlain, to avoided sedimentation, erosion, water supply, water quality, flood regulation follows a hydrologic pattern, lots of things like this. So you can repeat these. And then this one right here, number 4, where the provider is sitting out here like a big buffer, and then some beneficiaries over there. Anybody think of an example of what might use that flow pattern?
Islands they used to have outside of New Orleans, stuff like that.
Huh, that's true. There would be that, yes.
It's kind of like carbon sequestration too, in a way, right?
Not quite. Carbon sequestration is a many-to-many connection.
Mm-hmm.
Everything, all providers are connected to all beneficiaries via uniform atmospheric mixing. Uniform atmospheric mixing. That's for Bob.
Buffer strips on streams, is that it?
Sorry?
Buffer strips on streams?
Yeah, absolutely. That would be an example. Or like what Josh threw out there, coastal storm protection. So this could be a mangrove forest along the coast. It could be a coral reef. Anything that blocks a storm surge or a tropical storm. So you strike that, the storm gets depleted, and then it protects all the people on the right side of the beneficiaries.
Views.
Views, exactly, same kind of thing. If you have a nice view there, it might flow out to all the people who can see it on that side. Exactly. So the point of this is simply to say that ecosystem services flow from landscapes to people, right? And the means by which they flow, even though we can list off lots of different ecosystem services or benefits that we receive from ecosystems, you can often sort of group them together by flow category, which is nice because that kind of simplifies the simulation task a little bit because you only have to have a certain number of flow algorithms in place. Now if they're talking about things that are flowing, what is flowing? So we got to go a little bit deeper than what we're looking at right now in the literature. So we introduced a new term. We call this the service medium, the matter, energy, or information that transmit the service between locations, from the landscape that provides it to the people who receive it. So for any given service, you can think about it a little bit, and you can come up with the thing that would be the service medium. So I'm going to throw that out there to you guys again. So we're looking at water supply, like clean water supply. What's the service medium? This is a tough one. Water, yes, right, exactly. Okay, that's easy. Okay, how about pollination? What's the thing that moves from here to there to transmit the service? Bees, right? Or insects, or birds, or bats,
Or the
right?
air.
What's that?
It's pollinating to the air.
It could be air, absolutely. You could have prevailing wind currents for wind-blown plants. Exactly, that kind of thing. What about views? View of Mount Mansfield. What's the thing that moves from there to here and transmits the beauty to me?
Light rays.
Yeah.
Light rays, right? Exactly. We can simulate all of these things, which is great. So in all cases, we identify for an ecosystem service the source of the service medium. So it's the beehives. This is the landscape where the rain falls, right, distributed by some precipitation map. This is Mount Mansfield, the source of beauty, et cetera, et cetera. You identify the service medium, the thing that moves, and the flow pattern that it follows. The pattern, bam. And then you simulate its movement over space and time through this delivery channel to one or more users. Everybody got it? Pretty simple. Okay, stellar. Pretty pictures for examples. Yes, service medium, water, follows the hydrologic cycle. With carbon sequestration, you're looking at the service medium as carbon dioxide. It goes up, it goes down. Atmospheric mixing, which we will say is uniform, and if we want to get a climate scientist in here, or a meteorologist, they can make it a little more interesting with a really big simulation. But in general, carbon goes up, carbon goes down.
And I was actually thinking your arrows, I mean, it's your beneficiaries, the arrows go the other way, don't they?
Yes,
Yeah.
exactly. Now you're thinking, Josh Farley. Here's the pollen example, and of course, pollinators are moving this pollen from here to there, which is all good. Another one, I didn't throw out there. Obviously, wildfire protection. We've got a big issue with that in the West. So in that case, the source is identify the landscape that generates the service medium, being wildfire. That is what?
You mean ecosystem? I mean,
Fire-prone ecosystem, fire-prone landscape.
Vegetative fuels.
Right, vegetative fuels. fire-prone landscapes. Bam. So your source value for wildfire is going to be your risk for wildfire. So you can bust out a map of that. Bam. That's the degree to which wildfire will likely emanate from this location, right? Your service medium, matter, information, energy, moves. The wildfire propagates. We do a combustion or propagation algorithm, make it stochastic, have some fun with it. And then boom, you make a fire, and it strikes people. Property. Generally bad things. Small animals. It's not good. And then thereby you get this service transfer. But wait a minute, is that a service? Is it a bad thing? Let's think about that for just a second. And here we get this more abstract thing, where again we have scenic beauty. It emanates from some beautiful place, it flows by line of sight, it comes to me, I'm a person. Excellent. So we have views, they're great, they improve my quality of life. If only I could put a market value on them. Shucks. Okay, so people have different relationships with the service medium, right? Because sometimes the service medium is good, drinking water, right? It's generated over here via precipitation, runoff, snowmelt, springs. It flows via the hydrologic cycle. People encounter it, they grab it up, they drink it, and they go, ah, that's refreshing, right? It's great. This is good. The more water you receive, the happier you are under the conditions of diminishing marginal returns. However, the service medium can be detrimental. Floodwater, same source, almost the same flow simulation, right? Water moves along. People encounter it, but in this case, encounter with the service medium generates negative utility. It depresses quality of life, right? So sometimes medium good, sometimes medium bad. Same simulation, same framework. There's the negative sign. Now you guys see where I'm going at? So wildfire is a detrimental service medium. You generate it, you move it. So how do we calculate the service then? Where's the service? Okay, so we got to throw an extra piece in. So here is the abstraction that I'm getting at. It's a network flow abstraction, okay? So we have a landscape region. We call it the provisioning region or the source region. This is abstract, obviously, so they can all be in the same place, right? Depending upon the particular flow paradigm. So this is like Mount Mansfield or something, in the case of beauty, right? You put it up there, it's beautiful. It generates, in situ, some quantity of this service medium. We're trying to estimate that with some function. And then it's going to move across these flow paths, that's what the arrows are here. The thickness will indicate the amount of the service medium moving, emanating in different ways, okay? And when it goes across the landscape, it goes to users in brown and blue here. Two types, rival users and non-rival users. Everybody know the difference between rival and non-rival? We need some service? Josh, don't even worry about it. You guys there? So the difference has to do with, in this case, whether or not the person's use of the service medium depletes it from the flow path, right? If you use it up destructively, it's rival. If the service medium goes through you and you get an increase or decrease in quality of life without affecting the actual quantity of the service medium, it keeps going, non-rival in that case. And there you go. So you flow it through. So see the thickness of the arrow, it gets thinner through the rival use region on the top. Yeah, that's intuitive, right? You like that. Thick, thin, rival user. Excellent. Otherwise, it's the same thickness coming out of the non-rival use region here, and in another case, it just sort of all flows in the non-rival use region and disappears. Okay. Note the orange thing in the middle, or yellow, or whatever you want to call it. Okay. Sink region. This is the new piece which you have to add into this in order to get a bigger picture of beneficial and detrimental flows. So you can have landscapes which generate the service medium, sources or provisioning regions, and you also have landscape features which suck up, absorb, impede the flow of the service medium.
Billboards.
Billboards, visual blight in the case of line of sight, okay? But this could also be your evapotranspiration and soil infiltration in the case of hydrologic cycle models, right? Or it can be any kind of a landscape buffer like a dirt mound hill, a dune, water for blocking wildfire.
I was curious if you could somehow, because another way, like you could almost envision the trees, planting more trees, that suddenly becomes a sink. Now you've trapped your humidity in there and you're not going to burn.
Right, so
it's usually the opposite, at least in the West. If you thin your
yeah, like the ponderosa.
Yeah.
Yeah, so how would you then, how would then thinning be a sink?
Exactly. So there's two pieces to this. There's two pieces. So, we make a distinction between them in this framework. One of the things we might be doing is trying to put in something that actively absorbs or depresses the service medium's propagation, right? But the other thing is we might try and rechannel or sever flow paths, okay? And those become a little bit convoluted when you're dealing with wildfire, in that particular example, because it doesn't have too much, which is a sink by and large. Mostly it's just the flow path stops when it strikes a certain kind of thing. If it's possible for something to move for, You can make the distinction because if the fire can actually move through the location and keep going, but is reduced in intensity, then that's a sink. But if it is entirely stopped, then it's going to be just a severing in the flow path, and you don't go any further. So one affects the topology, and one is merely depressing the simulation values. So, different things. But you can see like this, the water one is easier to visualize from that case, or the visual blight, things like that. So you flow it, and you have sinks. So a priori, we can go in and identify source regions, we can identify sink regions, we can identify users. They're all potential things. We don't know if they're actually going to interact with one another because we don't have the topology.
And just one final question, like in the two examples that are, so in your provisioning region,
yes.
Could you have like so say the provision is wildfire regulation, and in the case of Austin gave, that means thinning the trees. So do you have like some probability that the thicker your trees, the lower your probability that you're providing that service?
Now we're going to have fun with the terminology and sort of mess with your head a little bit. It's still the source of the medium, right? The service medium, not the source of the service.
Right.
That's what we have to keep in mind. So the thing that moves, right? But the service is detrimental or beneficial. In the case of wildfire, you're flowing a detrimental carrier. You're moving a threat. Therefore, the thing that provides the service is the sink. That's the thing that provides wildfire regulation or flood regulation. In the case of provisioning or beneficial flow, in that case, the provisioning region is the good thing. And sinks are bad because they prevent you from getting more of the thing that you want. So it has to do with where you assign value, to sources or to sinks in the landscape. But it all has to do with how much provides the user. Any other questions before I keep running with it? Because I'm going to go into this in more detail.
That's kind of like water quality too, right? Where you have something generating clean water and then the sink is actually could be polluting it.
Exactly. So in that case, the sink, exactly. So you have like a 100% water quality value, or whatever it is when it starts. And when it hits there, the quality value gets decreased as it hits pollution locations. So in that case, the sinks are bad, the sources are good, and then we want to assign the negative value to the sinks and the positive value to the sources.
So if you're trying to find the ecosystem service value for thinning,
yep.
Right.
It's going to have to do. It's going to have to do assessing sinks. I'm going to show you actually some really cool maps.
Even though it's also at the source. It's both the sink and the source.
There's two parts to this, right? Because I don't want to conflate a baseline assessment and a scenario. Okay, if you thin something and then rerun the scenario or the assessment, and you compare two scenarios, one in which you had a depressed source, then you can say there's this much more service generated in this case than in this case, or this much less threat in this case and this case. But that's a scenario delta as opposed to a delta due to the current configuration of the landscape. So we do a baseline assessment and then we do scenarios for either increasing or decreasing sources, sinks, or rechanneling flow paths. You guys got that? Awesome. So review of the terminology. The service medium is the amount of energy information transmits the service, benefit or detriment, between locations. We model them using network flow and agent-based models. So this means that I take some water, so I take some bees, or take some fire or something, and I create little guys, little entities, which have a weight and a route value. So the weight is like a little bucket holding some fire or some water or something like that. And then they run around the landscape following their flow algorithm, and they try to dump it onto users while the sinks try to suck it up while they run across them. So we simulate it with a bunch of little moving guys on the landscape.
Sounds like Pac-Man.
Exactly, something like that, only with lots and lots of them, sort of like Pac-Man with ants. And then as they're running around this landscape, each location has three properties: its source, sink, and use value, which represents the amount it's going to generate, the amount that it can absorb if a carrier runs through there with the service medium, and then the use capacity and whether it's viable or non-viable, of course. So that's sort of your demand value, right? So you're not going to take any more once your demand is saturated, that kind of thing. So then we put it on a map. You see the fancy grids underneath there, graph paper, whatever you want to think of it as. And so we can keep it strictly pixelated, and in which case I don't put the polygons on there. And then we assign a source, sink, and use value to every pixel. And then we move it all around. Or sometimes what you can do to reduce the complexity of these calculations is you can exploit the piecewise regularity of landscapes. That was a big word. It means that when you're looking at landscape level variables, ecosystem type variables, typically you're not going to see a lot of random values really spatially close to one another, spatially proximal. That is to say, if I'm moving across landscape looking at land use, land change, I'm not going to see in adjacent pixels, I'm not going to go forest, field, forest, pasture, pasture, stream, river, urban, urban, street. Right? It's not going to be just kind of a mishmash of random colors. It's going to be sort of, oh, there's some forest, and then over here is a city, and then pasture, and water body, like this, right? So there's some regularity to the landscape, some regions of homogeneous values, at least within some epsilon, right? We can get that idea. So you might want to exploit that and try to segment the landscape up using any number of segmentation algorithms to try and just sort of break it out by, say, source type or sink type, things like that. You could do this for folks who are hip to the jive. You could be applying some spatial multivariate classification algorithms or clustering algorithms to try and do the segmentation based on all the variables that would be important to the source function, the sink function, the use function, just put them up that way. Okay, and then assign the values to the polygons, and then in that case, you would just apply, you do these sort of aggregate flows between regions with the arrows representing the direction of flow. Excellent. And in this diagram, sort of, you could imagine the dark ones are sources, that B, gray colored thing, is the sink, and the guys with stars, C, E, and H, are going to be use locations, and D and G have neither source seeker use values in this case. So you generate the thing, it kind of moves around, you know, some folks will be affected by sink B and some folks will not. Have you seen that? So like some people get an impeded view or something like that, and some folks don't, or some people get flood protection and others don't, or some people get wildfire protection and others don't, and so on and so forth. Bob here.
Okay, speaking of the jive, is this going to be a two-dimensional or an n-dimensional activity? Because
okay.
This shows nearest neighbor interactions.
It does.
To coin a phrase. What about CO2?
Absolutely, absolutely. So check it out. Ultimately, at the end of the day, let's go back to the text. Source sink and use values are computed by region or pixel. So in sort of in situ calculations, these are invariant functions, inarity functions, okay, for the input values required for those functions, and we're compressing them into a specific value. It's a categorization algorithm. Then each region or pixel is mapped to a vertex in a graph. Okay, a graph means bubbles and arrows. Everybody. The words are technically vertices and edges, but bubbles and arrows. Okay, each region or each pixel will be a bubble, and then the arrows represent a potential flow path between those regions. Okay. Now, to get to Bob's question, the orientation or the connectivity between the nodes depends on the flow algorithm. In this case, we're showing nearest neighbor interaction because this would supposed to be something that would be moving in nearest neighbor interaction, like water. It has to move from one pixel to the next, like so. But if you're looking at something like carbon sequestration, what you have is a many-to-many connection. All source points are connected to all use points, right? So you can make what's called a bipartite graph, where you will put all your source nodes here and all your sink nodes here, and you connect them all many-to-many. You guys have all done this with those questions on your test, where it's like draw the arrow from the left side to the right side to connect it all. Except imagine connecting everything to everything. Cool. So that's how we would handle non-adjacent connections. But well, that's how you connect many-to-many. But you can also do non-adjacent connectivity in this as well, because there's no reason you can't connect one node to another at the end of the day, because it's on a graph. This would be in the case of something like, let's say recreation, where you have a user, and the user moves via some transportation channel, like a train or a plane or something like that, from here to the recreation point. Right? They're going to move user to the source. So it goes the other way around. And in that case, we don't necessarily need to model every little piece of land that they go over. We could just model the train stations, for example, or the airports. Right? They go from here and they go here. They go from here to here, and then they get a car here, and then boom, they're at the thing. And they're at the park. You guys got it? So you can make it, you can keep as much granularity as is required for the simulation. Okay, here we go. So this is like an image of sort of graph with some really funny looking edges. Okay, so the big bubbles are going to be at each of the locations, right? And then the lines between them are the potential flow topology that we've expressed. Okay, we figured that out using a little spatial analysis, or saying, oh, it's CO2, connect everything to everything. Okay, and then I put a little square and a little tiny circle coming off of each one of those. Those are going to be little caches at each one of these locations, little buckets each node has associated with it, okay? And they're going to fill up. We're going to say that the green one is the sink, and the blue one is the use. Like two little buckets, they each have a capacity representing how much you can absorb, and how much a person can use there, what their demand would be. And then we, okay, edge represents cell-to-cell transition probabilities, and they have these values. I already said this. Okay, so there it is. We drop some service medium on one of these locations. Now, for the purpose of you being able to see it, I'm only going to move it from one source location, but of course I run it from all source locations at the same time, we sort of synchronize them, time step stop. But, okay, so we got some source. This is the fire started. Oh no, something like that. Or here's the water, or the bees, or whatever it is. And then they move, time step one, according to the flow algorithm, to their other nodes they're connected to, which may or may not be adjacency relationships in real space. And then, bam, maybe at this location up here, there was a user which grabs some of it and depletes the service medium along that path. Over here, another user grabs some, and some gets sucked up by the landscape in that location. Okay, and what's remaining moves on and may merge, and go on its own path, and we repeat. Maybe there's a sink there, and there's a user there, boom, here, and then, okay, a little bit more, and it keeps going. Now, the flows continue until either the flows get trapped topologically, that's like water hits a low point in the landscape, can't go any further, or falls off the map, or the service carrier runs out of the service medium. It's all been sucked up. Right? So we just simulate all these guys, they do their thing, and at the end of the day, we've collected all this cool information and stored it on this network. Now, I'm only showing a tiny, tiny bit of it. In this case, sort of this, what's the total amount you sunk, and what's the total amount you used? But that's not really the way I'm calculating it.
How many iterations do you do for each flow?
You run them all together, and you iterate them until one of those termination conditions are met. Okay, keep going until they stop because you can't flow anymore. So that depends on the spatial complexity and the topological complexity of the network. Okay, so we run it. We get some cool stuff, but it's not just this, because really each of those carriers has that weight value, saying how much it was moving around of the water or the fire or whatever, but it also keeps track of its route. Every carrier knows the full path that it took through the network. It knows all the sinks it encountered and the amount that each sink took away from it, and it has a record of all the users that it encountered and the amount that each user took away from it. All that information is stored on each use location when they're encountered, which allows me to then do some really fancy analysis functions, post-simulation analysis functions, on the carrier information stored on each user, the route data, and I can use that to generate a ton of really, really cool maps. Specifically, 16 output maps come out of the simulation for every ecosystem service, telling you a bunch of different facets of it, spatially distributed in different ways. And here we have this amazingly low-resolution diagram that depicts abstractly what you're trying to compute here, which is ultimately a many-to-many connection between all the source locations, the sink locations, and the use locations, keeping in mind that one location may belong to any number of these sets, right? But the idea is that each of these edges here would represent some number, a weighted value. So, and I've labeled some of them plus, some of them minus. So we say, in one direction, straight across, blue to red, we have this positive value, positive weight, which says how much the service medium did each source point contribute to each use point. Yes. And obviously vice versa. Secondarily, we know negative value. How much of the service medium was blocked from getting to each user by each sink point? This is important for all those regulating services when you want to assign a value to the sinks instead of the sources, right? And then, of course, how much of the service medium went into each of those sinks from each source point before it captured it. So that kind of thing. So this is sort of what you have, and a lot more, because you have all the routes as well as the weights. Okay?
If I could just ask quickly, so
Please.
going back, using an example of you have clean water flowing, and
Yes.
then it's being polluted.
Yes.
Would you look at that pollution as like a sink?
Yes, it's a
Okay.
quality sink.
So it's quality sink.
So I start with some 100% quality, and the quality gets depressed, or some unit of quality, and the quality gets depressed.
So
That's how we do
then,
our water quality model.
so then is the quality flowing? Is
Yes,
that,
the quality is
that's
flowing.
the medium or the
Yes, the water
itself?
quality. You're simulating the movement of the water, and your carrier in this case has two weights. One is its quantity, and one is the quality. And then you may encounter different kinds of sinks. You may encounter a quantity sink,
Right.
and you may encounter a quality sink. So it's possible that as a result you can receive a small amount of clean water, high quality, or a large amount of polluted water, and you might get the same value as a result.
So the
Right.
water flowing, so there are two types of sinks. So like dirty
Yes.
water flowing over a forest, that's a good sink.
Yes.
And then flowing past a sewage plant, that's a bad sink.
Yes. So it goes up and down.
What about when the sinks are not discrete, like constant evaporation rate?
Sure. So this all has to do with to what degree you want to run these simulations at, obviously. So you can do a couple of things with this. Obviously, this would bring us all the way back to that one. So if we're looking at something that's, evaporation rate is not going to be constant everywhere necessarily. So you might be able to, again, segment your landscape over some region and then say I apply the same value over this. You might choose to do it discretely, or you might choose to apply just the value over the region and then move to the next. But this obviously will depend on the granularity of the calculation. So, I mean, with a lot of these things that are more continuous processes, for the purpose of these simulations, we've typically discretized them and then tried to apply them on a per cell basis or a per region basis.
So, I mean, I'm wondering, could you have multiple thematic sink overlays that are
Yes.
that are
Right.
intersecting?
Yes.
So your
sometimes.
forest could have evapotranspiration reducing quantity and purification increasing quality?
Yes.
Yeah.
Quite right. So that happens. So at each step, obviously the carrier's weight values they go up and down depending upon what's going on there. And different amounts get stored and assigned to different people. Okay, results of a flow analysis. These are some of the things that you get out of there that you can infer from these 16 maps that we generate. Okay, so one are the benefit shed maps. So it's a new term, not really, not for you guys. Hand.
So, just curious about what you're measuring here. So you have your benefit shed. Depending on the service, that's a different unit. So like it's pollination, your benefit shed is measured in bee population number, or like
pollen transmitted by bees.
So
it's the pollen, right? That's important. So go from here to there, kind of a thing. And without the bees, which are the agents, the carriers moving it around, it doesn't get around. So yes, you're looking at essentially amount of pollen that's being deposited per location.
Okay,
that
so
kind of thing.
Each service is being measured. Like none of these would be monetary, basically.
Right. All of these are flow of the service medium, right? Which is beneficial or detrimental. Applying a value on top of that is the next step that you do at the end of the simulation. But the purpose of this work is to try and connect together on a per region basis. You want to be able to answer the questions, where do I, user, get my services from? And the other question, who gets services from that piece of land? So we really want to get the spatial connectivity piece in there, because then we can actually say something about who's liable for different services, who's dependent upon which things, who's going to lose in the event of change to a public good, et cetera, et cetera. Who might want to target for a PES strategy, all those kinds of things. What land should be kept in conservation if you're a government entity, et cetera, et cetera. So one question we answer, to where and whom the benefits from each region flow, per region. We can do this. Weighted. It's quite nice. Cool maps. Provision sheds. The other way around. I look at each user and I want to say, what is the source of my ecosystem service benefits? I get something from these wetlands over here, and I get something from the forest over there, and the rest of it doesn't provide me anything for this service. But then for a different service, maybe I get a little bit from there, a little bit from here, and so on and so forth. So for each service, each user has a different spatial distribution of its sources. Flow interruptions, these are your sinks and rival users. So the things that get in the way of the medium getting to me, for good or for ill, right? That might be good when it's a bad thing flowing, in which case I assign value to the sinks. Those are the things that provide the ecosystem service for regulating benefit. But I want to know who's up there blocking that stuff from getting to me? Who's protecting me? What landscapes are protecting me? And which rival users am I competing with? If you need to think about issues of water rights and whatnot, for example. And of course, because we have all these routes, we can overlay and we can get these flow density maps, which look pretty fancy, and show you where it's all moving, right? This is like wildlife migration corridors. Right? So we want to look at which areas exhibit the greatest flow density, and then think about substitutability between those different paths, because that brings a whole new dimension to this problem, which is not, if I want to protect ecosystem services, I have to protect this landscape which generates this service, which I've now said has to be a source or a sink in a flow simulation in order for it to count, and the users have to be somewhere at the end of that flow path. So now we can get a little bit more granular, but you also have to protect the flow paths themselves, even the areas which are not sources or sinks, because if you don't do that, service never makes it to anybody, service is never realized. And then you're protecting land that doesn't give a service, for example, because something else got in the way. Okay, and then you can use this stuff to inform policy, right? You might say, okay, well, maybe I don't want to actually do anything with the landscape, but I recognize that there's more potential service coming through here than is currently being tapped. So maybe we just need to get better technology or better institutions to access the resources that's actually moving through currently. So that might give you some targeting plans from the human side. Obviously, you can manage landscape to create greater source values, keeping the flows and the sinks the same. Call it good. That's probably the best thing anybody's going to do right now. You can decrease sink effects, right? So, oh, geez, that thing's in the way, and I really wish it weren't there. So fix that, not the pretty thing, right? What have you. That's what's messing me up. Or the other way around, increase sinks, right? If you need more protection. Or preserve sinks, whatever. You know, someone's going to take out your mangroves and say, whoa, 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 hold on. Those are really important regulating providers of service. They're flow sinks. Or, of course, you know, again, this is like your water rights issue where people are sort of fighting over a limited resource that's moving along, and people upstream of you get it all and you don't get any. So maybe you need to identify, wait, these people would be beneficiaries of a service if those folks didn't take it, but now I can see that given the flow channels.
Or increase non-rival use effects.
Or increase non-rival use
putting
effects.
patents on genetic information, stuff like that.
That kind of thing, exactly. And obviously, you know, if you're feeling gung-ho and you can do it and you have a huge plow or something, you can rechannel around flow paths. Irrigation. you know, among other things. So there's that. Or, you know, you can plant a nice corridor where your fire will go straight to your doorstep. That's just what I was hoping for. So, okay, to put it on a map in color and make it look pretty, here's Camp Washington. I know you guys can totally tell. Okay, so now in green, we're showing sources of beauty. Sources of beauty, right? Okay, yeah, that's kind of limited, right? But okay, a few sources of beauty. So up in the left here, that little bit, that's part of the Puget Sound sticking in. And here you're seeing Mount Rainier in the bottom right corner, and we got some other little, there's like Bonner Lake, and some little guys hanging out in the middle, little bodies of water there, and some little hills up at the top. So, that's nice. These are things that people like to look at, according to hedonic literature. They like big bodies of water, and they like big mountains. So, we find the things that are beautiful. These are going to be the sources of beauty. We drop some users. Bam, users. That's the property, residential property in Kent, Washington. Those people might acquire property value increases due to scenic beauty, right? And here is the visual blight. This is the commercial industrial transportation stuff, some highway action going on in there. It's great. This is the development. People don't want to look at that.
They're visual bads, but not sinks.
No, those are the sinks. That's the visual blight.
Okay.
Right? Green source, yellow sink, red use. But we don't know which things are in the way.
They actually block the view.
Remember, two pieces.
Yep.
Two pieces, right? If the view can go through, but gets depressed by a feature, it's a sink. If it cannot go through, for example, elevation is in the way, then there's no flow path. So that's a topologic severance. Okay? Two ways the service cannot flow. Okay, so in this case, these are just things that are not pretty.
It's adding nasty photons.
Exactly, nasty. It adds photons of ugly. So that when I look, I get some photons of happy and some photons of ugly. And then it's the general proportion that's important, wherever my threshold lies.
So like a sink would be, you know, you're here, you're in your apartment, and you can see Mount Rainier, but you also see like the highway.
Yes, there's a highway, and there's like a great big sewage plant. You know, fantastic. That's what I think of every time I look at Mount Rainier.
Have you read At the Shrug, where they describe the beauty of the billboards and factories in the Wisconsin countryside?
So I've had this discussion with people before. So in that case, remember these functions have to depend upon the user, right? So in that case, you just change the source function to say, I love billboards, and highlight them in green. Okay? And oh my gosh, there's a pond, there's a park there. Whoa, yellow, yellow, yellow. I hate looking at those things. Oh, they make me feel so sketchy and alone. So, that's no good. So you identify the things which are beautiful and which are not beautiful in terms of the user. Boom, lay them down there. But these are only potentials, okay? They're in situ. Calculations, per pixel, per region. I don't know if anybody has lines of sight through those things. You guys getting where I'm going with this? You have to do the flow simulation. Okay, so boom, we throw some light on it. Oh man. And as always, it looks terrible on the projector and looks better on my screen. Isn't that the way it is? Anyway, there's light, I assure you. They can see Mount Rainier. But you can maybe sort of kind of just see it, and they fade out is the point. There's these beams of light shooting from all the green areas in the landscape, and they're fading out. There's a distance decay built into this, okay? Continuous distance decay function. It's being applied. And if there's elevation in the way, there's no path. The light won't be projected. If you try to shoot the beam, it gets blocked by something, then I just take the beam off the map. So you're only seeing things where there is actually a view, and there's more than this. The middle one has a little beam going up. Mount Rainier has a big fat beam that sort of fades off, gets kind of thin around the green guy in the middle, and this guy up here fades out. And you can see some parts of it are lighter than others. These are the pieces which are more in people's view line than other things.
Could you have like smog adding, you know, reducing your you're reducing your light flow?
Exactly, exactly. Yes, you can apply smog, and smog becomes a view sink, a continuous view sink over the landscape. And that's exactly what you do. And then you can use that to then say, okay, this is the amount that depresses it in a different scenario where I reduce the smog, views get improved, and everybody gains more service, because more of the medium gets through. You guys get it? And then you can say something then in units about, even if they're abstract units in this case, of the effect of reducing the smog on property value, for example. You guys feeling me here? So I might turn into contour maps, just for kicks, in which case you can see more generally which areas have really high, where lots of lines of sight go through. That's the point. This is where the views are. And actually on this map, it's a little unfortunate because I think I had the decay up a little bit too high. But if I reduce that decay function, these things all project further. But anyway, the point being, this is showing you the flow density over the landscape, right? So this helps you for targeting decisions. So I need to put my Walmart somewhere, my billboard somewhere, so don't put it in the red and the yellow area up there. If you do, you're going to get in everyone's view. You put it in these areas with lower flow density, you're not going to interrupt as many views, right? So if you have to drop something that's going to be a sink, and you don't like sinks because it's a beneficial carrier, put it somewhere where you have low flow density, and then you won't interrupt any people's service. You guys get it? That's the idea. However, the other way, if this is something really bad that's moving, then you want to drop the sink right in the red spot, because that's going to have the biggest impact on the most people if you have to target, because you know you always have cost constraints, resource constraints. So that's the idea. So this is your critical flow paths map, as it were, for example. And then show them in black and white, because you know black and white is cool too. So line them up. These are all the same location again. Here's your source values. You can see them better in these, I think, than in that last overlay. So that's the source areas. That's Puget Sound, Mount Rainier, the other nice pretty things. That's the theoretical sink. That's the theoretical use. I use the word theoretical because we don't know if any of these things actually provide service, if any of those guys actually get any benefit, and if any of these things are in my way. Check? Okay, we flow. Bob Harrington, you have a question?
Theoretical use is what?
Residential.
Residential property, in this case. People who might get property value increases if they had a nice view. Because that's all we're caring about in this case. Okay, we flow it. Okay, boom, it moves. I should probably reduce that decay. But anyway, it flows. Everybody aims their source at the user. This is line of sight projection. It's a raycasting algorithm. It gets blocked by elevation. You know, this is pretty simple. Bam, that's possible flow. So I'm making, here I have a little fun with this. So we run the simulation with and without the sinks. Possible flow is without the sinks. So it's an upper bound on the view. And the actual flow is where it is now. So without sinks, with sinks. And then we take the difference, possible minus actual, and you get the blocked flow. That's the contribution of the sinks to succulent flow. So that's the flow of beauty, and where it goes, and where it's coming from. It's being intercepted by sinks, which are all sitting up on the top of those lines. Okay? So that says just how much the world has been changed by your sinks. You can use that to talk about water, flood water protection, fire regulation, etc., things like that. Then we back aggregate them up. So I take the amount they got from each source point to a user, the amount that actually it reached a user in the non-sync case, and this is the non-sync case. But then I have another map called actual source, which shows it in the sync case. Okay? So you have theoretical source, which is this upper bound value, then possible source is the amount that each source value actually contributes to any user without sinks, and then how much it contributes with sinks. So we back aggregate and say which things are actually beautiful in this case, which things provide view benefits, which ones don't. The users, in this case, same guys, basically everybody got a view in this case, without looking at it a little bit more closely. So that's who receives views and to what degree. The darker pixels are the ones who have better views. Okay? And the actual sync, this is the actual visual blight that's really in the way. And the darker it is, the more people it's damaging. Excellent. Okay, now I might set them on top of each other so you can see. See? Theoretical source. This is theoretical sync. Theoretical sync. Yes, actual sync, not possible sync, because obviously there's no possible sync value if there's no sinks in the simulation, right? Right, okay. Yes, so just the actual sync, because it really matters here. So bam, that's the part of the sync that really counts. So now you can actually say something more informed than the top row, or actually the top left, which is most of what people are doing right now. That's beautiful, preserve it, give a dollar value per acre of pretty mountain. I say, wait, only certain areas help people. These are the ones that really are helping right now. The other ones are unrealized, but could be realized if you, the difference between possible and theoretical is called the inaccessible source. That has to do with the flow topology. You have to add new flow paths in order to increase possible to theoretical. The difference between actual and possible source, which I'm not showing right now, is the sync value. You have to depress sinks to increase the value from actual to the possible value. And so this informs two different policy options. And then you see which sinks you have to actually pay attention to, who gets what, which is all very cool. Everybody's feeling it.
Those actual sinks, those are ones like, if we want to like rezone to get rid of those, those are the ones that are actually going to...
Those are the ones that are in people's view right now and are messing up their views. So if you take those out, people will be happier. If you take out the other sinks in the theoretical sync map, those are inaccessible sinks. Nobody has a view through those. So right now it's not actually affecting anybody for this service. Obviously other services are going to have different impacts. And then this is the last slide for Farley as he rushes out. Okay, so open problems and next steps in this problem domain. There's a bunch of them, it's fun. But this tries to get a little bit closer to getting values for ecosystem services. So one is you have to determine the upper limits on downsampling your spatial data sets that you're assessing for the source, sync, and use, and flow values. So the resolution you can run the simulation at is going to be restricted by the flow dynamics. Okay, you can't run at a coarser resolution than what you need to see stream channels if you're trying to move water, right? Otherwise the water goes the wrong way. That kind of thing. But some of the services are a little less, they can be run at higher resolutions. So to find the right resolution to run this thing out, the coarsest resolution you can run out I'm working on developing an algorithm to try and figure that out in an automated way for any given service, if you can describe the flow dynamics. And then that will help us speed up computation time for these things. Furthermore, for doing things like recreation, and if you want to transport food and all that kind of jazz, you want to do flow path analysis along human transportation networks, which likely means partnering with the transportation center. And so fortunately, the guy that works with me upstairs, Brian Boyd, is one of the transportation guys here. So he does the urban simulations. So in that case, you need to move the service medium, the people, through the transportation networks to the service, like the recreation, or the food the other way. Okay? So that would be fun, but it's a whole new problem domain, and then simulating things like water flow or wildfire flow, right? Natural system processes. And if I tell you where the flow paths are, which ones are, so that tells you part of it. We also need to know the substitutability between paths. So if I drop something here on this area where there's a lot of flow moving right now, given the current properties of the flow, can it redirect itself through a new flow path and still have everybody still receive the service? So how substitutable are paths is important. And if you find that a path is not substitutable, if you sever it by dropping a sink in the middle of it or changing the flow topology there, you're going to impact everybody irrevocably because the flow can't rechannel. Then you understand that there's no substitutability, and therefore the value of a flow path becomes more valuable. So, flow path substitutability is an open problem, figuring out how to calculate that. And then the holy grail of this would be to actually, once you've got the substitutability down, and you've got the human transportation networks, and you've got the resolution to run at, what you'd like to be able to do is step in and have a spatial optimization algorithm that will help you figure out that, given my cost constraints or resource constraints, what are the optimal targeted landscape modifications that I should make, which would affect sources, sinks, and flow pathways in this case, should I make to try and maximize my service delivery to the beneficiary groups that I care about. So you want to have an optimization algorithm for that. And so these are some of the problems that I'm working on, all very cool things. And this funding comes from the National Science Foundation, a grant with a number, in the way that they usually come. I have some advisors. This guy who's now in Spain, Ferdinando Villa, but he's Italian, so not the name. And then Robert Snapp, who's a specialist in artificial intelligence and pattern classification and things like that, neural networks and whatnot, over in computer science. And some of my fellow members on the Artificial Intelligence for Ecosystem Services ARIES project, these folks. Farley, who ducked out there, yeah, he's right there on the end. And then we have a couple of NGOs who work with Conservation International and Earth Economics. You guys may or may not know them, and I have their logos there, which is fun. And we partner with them to do case study implementations of our system in Madagascar with Conservation International and in the Puget Sound with Earth Economics. That way we can work in a data-rich zone and a data-poor zone. That's kind of the idea there, to try and compare the approaches. And also people have very different value systems in an industrialized location and a really rural location. So that's the idea. And we have a third case study, which I actually put up there, which is with INECOL, the Institute of Ecology, National in Veracruz, Mexico, where we're trying to hit it sort of in the middle, right, of the rural to urban spectrum and the some data is good, some data is not so good spectrum. So that way we do the mama bear, papa bear, baby bear approach, and we sort of get it all. Right? And we just get it just right. And yeah, so that's the story, and I'm sticking to it. Thank you.